Hello again. In this video, we're going to cover section 5.3, which is called Trigonometric Functions of Real Numbers, but it's essentially a collection of basic properties and terminology that we're going to need moving forward. So, unless otherwise stated, all variables and angles are assumed to be in radians. Um, that's just an observation that we need to carry with us throughout this section. Okay, so first thing we're going to talk about is periodicity, and here I give you a definition of the so-called period of a function, if it has one. It is the smallest number k for which a function f satisfies f of x plus k equals f of x for all x. And now this is important, the for all x part, but then we call that k value the period. So this is what we're defining. The period is defined to be that k value. And so essentially what this is saying, and maybe you're familiar with periodic functions, but essentially what it's saying is if there is some fixed number that every time you add that number to your input, you get the same value. Okay, so coming over here, if you look back at your unit circle, you'll notice that you can go all the way around the circle, and every time you do that, both sine and cosine values will repeat themselves. And so I know that sine of t plus 2 pi, let's say, is always equal to sine of t, right? Because I'm essentially going one more full rotation around the circle from my current angle. And remember, our variables here are assumed to be in radians, so I'm adding radians to radians here. So like if t were pi over 2, and I add 2 pi to that, that's the same as just sine of pi over 2. So hopefully that much is clear. But now what we can say in general is that you can actually add any multiple of 2 pi. And the reason that is that now 2 pi n, where n is an integer, this is essentially saying this is allowing for multiple times traversing around the circle. So if n were like 2 here, then what I'm essentially doing is starting at my angle t and then traversing twice around the circle. So it would look something like, oh, hold on. So it would look something like, let's say here's my unit circle, let's say here's my angle t, right? So angle t. Now if I just traverse twice more around, well, I'm going to get the same exact sine and cosine values. And so, in fact, cosine of t plus 2 pi n equals cosine of t also. And this is, both of these are for all integers n. And if n is negative, then that just means you're traversing the circle clockwise, right? But you're still going around the 2 pi, because that's designated right there. And so actually, this k value for sine and cosine is 2 pi. So the period of sine and cosine, 2 pi. We'll get to the period of tangent later, but it is a little bit different. Okay, now let's talk about even and odd functions. So here's my best try at a unit circle. Let's say we have some angle theta and some angle minus theta. You'll notice that they're essentially the same angle, it's just that one goes counterclockwise, which makes it positive, and one goes clockwise, which makes it the negative angle. Now, one thing to notice is that, and I'll do my best here, their x values, i.e. their cosine values, are the same, but as we saw when we were filling in the unit circle in the last video, their y values are different, right? And in fact, they're opposite of one another. So what we're going to conclude here is that the cosine of minus theta, well, the x value, that's what the cosine is, that's the same as the cosine or the x value of positive theta. Now, however, the y values change, right? But they only change by being the exact opposite. So whatever the y value is up here, it's the opposite of whatever the y value is down here. And so we get this relationship here. And since, well, let's check this out. Tangent is just sine over cosine. So it's the sine of minus theta over the cosine of minus theta. Using the above, what we have is that the top is negative sine theta over, well, cosine of negative theta is just cosine theta. And so this is negative tangent theta. And so what we see is that this one is odd, as is this one, but cosine is even, right? And it turns out that cosine and secant are the only even trig functions. The other four are odd. So cosine and secant are even. Other four are odd. So sine, cosecant, tangent, and cotangent are all odd. So that's a neat observation. All right, now let's come to the graphs of sine and cosine in particular, and then I give the reciprocal graphs over here. But this this one's important. So what I like these four values: pi over 2, pi, 3 pi over 2, and 2 pi. So what I want you to do is to find them on either your unit circle or your chart. And now what we're going to do is we're just going to plot the sine of each of these angles. So the sine of angle 0 is just 0. So I put the value 0 right here. The sine of angle pi over 2, well, if you look, you'll find a value of 1. Similarly, the sine of angle pi, you'll find a value of 0. Sine of angle 3 pi over 2, you'll find a value of -1. And a sine of 2 pi, you get back to the angle, you get back to the output 0, right? And so the graph of sine, I think you can kind of see the picture, and maybe you're familiar with this, but it looks something like that. And then it just, it's going to repeat itself. And now we know that sine is odd. So when I plug in minus pi over 2, that's the same as plugging in pi over 2, but taking the negative of that answer. So I'm down here at -1. And similarly, 0, 1 for sine of minus 3 pi over 2, and then again 0 for sine of minus 2 pi. And so we get a graph that kind of looks like this. And these aren't hard corners here. I know it looks like I kind of did that. These are nice and smooth, okay? And now this graph keeps continuing. And so what we see is that the graph actually repeats itself every 2 pi units. Take this 2 pi chunk. If you just move it back 2 pi, you get exactly this chunk here, right? So that is the periodicity that we're seeing. Now, the graph of cosecant is, well, it's the reciprocal graph. So everywhere that sine has an output of 0, you're going to have a vertical asymptote because 1 over that is undefined, which we saw when we filled in the table, right? So here, sine has an output of 0, so we get a vertical asymptote right there on the axis. And again at pi, and again at 2 pi, minus 2 pi, etc. And now just doing the reciprocal, this essentially flips upside down and it kind of limits towards those asymptotes there. This one down here, the reciprocal of -1 is still -1, that's why that point is there. But then these values are negative, their reciprocals will still be negative, and they kind of point the other direction. Okay. So now let's look at the graph of cosine. Again, now we're just looking at the first column or the first entry, depending on if you're using the table or the unit circle. So the cosine of 0, you get a 1. The cosine of pi over 2 is 0. Cosine of pi is -1. Cosine 3 pi over 2 is 0. And cosine 2 pi is again 1. So you get something, this isn't a V shape. It is kind of this smooth, and then it continues like so. Now similarly here, cosine is even, and so when you plug in the negative, you're going to get the same output. So cosine minus pi over 2 is still 0. Cosine minus pi have the same output, -1, and so on and so forth. And so we're going to get this image here, right? And once again, we're seeing the periodicity that if, like, you take a chunk of length 2 pi and slide it around and overlap it, it'll match perfectly over another chunk of length 2 pi. And this is the reciprocal graph. We'll come back to these maybe in a later video. But what we're seeing is that everywhere that cosine is equal to 0, so pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, you get vertical asymptotes, and then you just do the reciprocal. So the reciprocal of 1 is still 1, that's why that point is there. But now the reciprocal of numbers less than 1 is going to be bigger than 1, and so that's why they kind of limit up towards the asymptote. Similarly here, reciprocal of -1 is still -1, but the reciprocal of negative numbers between 0 and -1 is going to be negative numbers that are less than -1, and so that kind of limits down here towards these asymptotes. And this just keeps going. All right, now the graph of tangent and cotangent, it's hard to see from the chart, but it kind of goes like this. So the tangent of 0, that much we do know is 0, and the tangent of pi you can also find on your chart is 0. The tangent of 2 pi is also 0. And in between, you get this kind of what looks like a cubic graph, but it's not exactly. And now we have asymptotes at every pi over 2. The explanation for that is that, tangent is just sine over cosine. So everywhere that cosine of x equals 0, you're going to have an undefined value, right? And that's exactly at pi over 2, at 3 pi over 2, at minus pi over 2, at minus 3 pi over 2, etc. Right? And the key observation here is that these two, and now this is just the graph of the cotangent, so take the reciprocal of all these values and you get something like this. This has period, the tangent and the cotangent have period pi, not 2 pi. Notice they repeat themselves every 1 pi units. So that's the key observation there. Okay, so limiting behavior. You're used to seeing this with a like an infinity here, like talking about end behavior. But now we can talk about it as we go towards like a particular number. Here, as x goes to pi, where are the y values going in the tangent graph? Well, here's x equals pi. What do the tangent values look to be? Well, 0, right? Now, this notation means approach pi over 2 from the right. So here's pi over 2. Look just to the right of it. What's happening to the tangent values? Well, they're shooting down towards minus infinity. Similarly here, look at pi over 2. Look to the left of it. Where are the tangent values shooting towards? Positive infinity. Secant graph, look to minus pi over 2. Look to the left of it. Where are the secant values shooting? Well, down towards minus infinity. And now here's 3 pi over 2. Look at the cotangent graph. Where are the y values settling? Well, right here at 0, right? Okay, and now the final piece to this section here. For which angle measures in 0 to 4 pi does sine of x equal minus root 2 over 2? And so what you're going to do is you're going to look at your chart. And so here's where we're going to leverage periodicity here. So first go down your chart and find all the angle measures in 0 to 2 pi. So go down the sine column, find all the angle measures that give you an output under the sine column of minus root 2 over 2. So it looks like the first one I see is 5 pi over 4. And then the next one I see is 7 pi over 4, right? But now 0 to 4 pi is actually 2 laps around the circle. So here's what I can do. To get my other 2, I just add 2 pi to each of these, and that would take me within 2 laps of the circle. Because really what we're doing is this chart only gives you within 1 lap. But angle 4 pi radians is 2 laps, so once, twice. So now the other one will be 5 pi over 4 plus 2 pi, which is 13 pi over 4. And then the last one is 7 pi over 4 plus 2 pi, which is 15 pi over 4. And now let's look down the tangent column. Let's find all of the angles x that give us a value of root 3 in that column. But now we want to restrict where we're looking only from minus pi over 2 to 3 pi over 2. So let's first find the positive angles. So here, I think at angle pi over 3, that's 1. And I think 4 pi over 3. And now once we get to angle 3 pi over 2, we stop, right? Now, angle minus pi over 2, well, let's take a look here. So angle minus pi over 2 is here, and now we're going all the way to angle 3 pi over 2, which is here. So what we have is this angle here at pi over 3. We got 4 pi over 3, which is this angle here. Now we just need to determine if there's any angle here which will give us that'll give us root 3 in the tangent function. And the answer is no, because in quadrant 4, which this is, which is where the angle would have to be, we know tangent is negative, so it can't possibly spit out positive root 3. Okay, so hopefully this helps on the on worksheet 15. In the next video, we're actually going to pick up with section 5.5. We're going to skip section 5.4 and jump right into section 5.5.